today's lesson, it's more like a tutorial. We will be working out one-dimensional heat transfer related problems. And once you get the hang out of it, I will post some lecture notes for you to go through the two-dimensional heat transfer problems and how to tackle with line and point sources. Since the methodology which is adapted in solving a finite element problem, heat transfer related finite element problem is quite similar to that of how is done with the structure related problem. I will only discuss one-dimensional heat transfer problems, and I will invite you to go through the formulation of the two-dimensional heat transfer problems, as well as how to deal with line and point sources on your own. To start with, let's look at a few simple examples for you to get a good grip of the theory which we learned during the previous lesson regarding formulation of one-dimensional heat transfer problem. So as the first problem, let's try to determine the temperature distribution along length of a rod. Assume that you are given, you're supposed to analyze the heat transfer along the length of the rod, and consider the rod has been insulated along the length of the rod, and the cross section of the rod, of course, is a circular cross section where the periphery is insulated throughout, so there will be no convection taking place to the outside environment. Let's assume the radius to be 1 inch, the length to be 40 inches, this insulated layer, and assume we know that the temperature at one end to be 100 Fahrenheit, and now we are supposed to calculate the temperature along the length of the rod, given the correct boundary condition. So given for the given boundary conditions, we would have to calculate the temperature distribution along the rod, and at the right hand extreme end it is connected to, let's say, the environment. So basically there is convection taking place at the right hand corner. So you are supposed to determine the temperature distribution along the length of a rod, and the boundary conditions which are given is the temperature at the left hand end, which is a constant 100 Fahrenheit, and the free stream's temperature is 10 degrees. Yeah, so we can call this T infinity 10 Fahrenheit, yeah, which is open to the free stream or the environment. And let's assume the H value, the convective heat transfer coefficient, to be H to be 10 British thermal units. So we will be using here in this instance the imperial units for you to get a hang of such problems too, or the units, hour per feet squared per Fahrenheit is the unit we have to use in imperial units, and thermal conductivity. These are the values which we require to calculate the conduction and the convection heat transfer coefficients when we talk about the heat distribution or temperature distribution along the length of the rod. 20 British thermal units per hour feet squared Fahrenheit. So the value of H is typically for forced air convention, and the value of Kx is typically conductivity of carbon steel in this particular example. So what do we have to do first? Our aim is to calculate the temperature distribution along the length of the rod. So first what we need to do is we need to develop a finite element discretization model. Let's say, to start it simple, Let's assume the total rod is divided into 4 elements having equal distances, each having 10 inches of length. And let's try to calculate the temperature at each of these points. So there will be convective heat loss only over the right hand corner, which is exposed to the free stream. And we consider the left hand to have a known temperature, and of course the perimeter of the rod to be insulated. Then after we develop the finite element formulation, let's say finite element model, then we can calculate the stiffness matrices for each element, then assemble the total structure stiffness matrix, apply boundary conditions, and calculate the relevant temperatures. Quite simple and quite straightforward. The same procedure which you applied when solving structure related problems. We need to first, let's develop a finite element discretized model. So this 40-inch rod, which we are interested in now, let's further exaggerate this view. Let's divide it into 4 equal parts. Similarly, a similar procedure to what we did in structural problems. We had to divide the total element to a certain number of nodes, and of course the certain number of elements, meaning resulting elements. So the periphery is insulated, the right hand corner exposed to the free stream, and on the left hand corner, let's assume a fixed temperature of 10 Fahrenheit. So we have 4 elements. Let's name them as 1, 2, 3, and 4. So the nodes would be 1, 2, 3, 4, and 5. One node extra to that of, let's say, the element number, and each element has a length of 10 inches. So it is the same distance for all these elements. First, let's try to calculate the stiffness matrices for each element. For that, we will use the equations which we derived previously. We know the element stiffness matrix can be calculated in the following way. The conduction, let's say, heat transfer corresponding to conduction, of course, there will be the element stiffness matrix will correspond to AKXF, cross-sectional area, times the thermal conductivity divided by L. So the area is given by phi r squared, that is phi 1 inch squared. Thermal conductivity is 20 British thermal units per hour per feet per Fahrenheit degree, of course, times, and of course, to multiply by feet squared, because now whatever we are dealing with is in inches, but to comply with the other units, that is here you can see the thermal conductivity is given in terms of British thermal units per hour per feet per Fahrenheit degrees. So whatever the length we have in this equation has to be converted into inches, so rather feet. So the inches has to be converted to feet. So this is what we done. What we are doing here on the denominator, we have 10 inches L, which also needs to be converted again to foot. That's 20 inches per foot, of course, multiplied by 144 inches squared. Yeah. So mind you, it is on the numerator, it's phi r squared, phi 1 inches squared. So this inch term, 1 inch squared term, has to be converted to feet. And on the denominator, we have 10 inches, again, the length, which again has to be converted into feet. So that is why we see this 144 value, 12 times 12, also appearing in the denominator. So what if there's the next block, let's say the next fundamental component which we require to formulate the finite element problem is the convective contribution. For the moment, let's write and keep it if not necessary. Let's not use it, okay, for you to, since it's the first example. So if there's convective term, the corresponding, let's say, the common factor would be the convective heat transfer coefficient, the perimeter times the length of the element divided by 6 is the common factor for such elements. So here again, we can use the convective heat transfer coefficient. The convective heat transfer coefficient of the free stream is 10 British thermal units per hour per feet squared per Fahrenheit degree, multiplied by 2π divided by 6. And since the length is in inches, that is 2πr, r corresponds to 1 inch. So let's convert that 1 inch again to foot, and the length of the element is 10 inches. Let's convert again into foot. So here, if you solve this, maybe I forgot to write the answer, you would get 0.5236 British thermal units per hour Fahrenheit degree. Similarly, you would get, so if you're working out this problem on your own, just like a tutorial, you can simply pause the video and try it out on your own and resume with the video, which would be quite convenient for you. Another term that we would like to include is the heat transfer, the common factor of the matrices of the heat transfer finite element formulation problem. It's a contribution from the free stream convective contribution occur due to free stream convection, which is open at corresponding to the surface, open at the right hand side, which we can write it down as h times the T infinity times the perimeter times the length of the element, 10 British thermal units per hour feet squared Fahrenheit degree is the unit of interest, or is the unit in imperial units, and the temperature of the free stream is 10 Fahrenheit degrees. We had multiplied by perimeter 2π, 1 inch, 2πr, r corresponds to 1 inch, which has to be converted to feet, and the length of the element is 10 inches, again converted to feet. You would get 43.63 British thermal units per hour. Good. Now we have all the corresponding conduction components corresponding to conduction and also convection. Conduction, convection from the element, and of course convection to free stream. We have three, let's say, common factors which we require to develop the finite element formulation. We can use now the equations, let's say 9.422 and 9.427, let's say, which we derived previously in the previous session, and of course write them down. We can write the total, let's say, considering an element, we can write down the element stiffness matrix. Let's write it down as K. Now includes two parts, or let's say all three parts. The conduction part multiplied by here, of course, 1 minus 1 and minus 1, 1, which is symmetric element, plus we have another term. If there are any convection taking place, this is the matrix formulation that we already obtained from the previous session. If there is convection to a free stream, you know, it's a, let's call it the convection from a free end, has to be multiplied, where the convective heat transfer coefficient has to be multiplied by the shape function transposition of the shape function, have integrated over the surface. So now we can substitute these equations for obtaining the numerical values of the element stiffness matrix. So the element stiffness matrix for the first element, let's write it as K1, is, so we simply substitute the values now. 0.5236 is the value we obtain for this AX, A times KX divided by L, this section, multiplied with the corresponding matrix. All right. So here, of course, it's clear when we consider element number 1 that the second and third terms, which corresponds to, let's say, convection and convection from the surface, of course, and convection to a free stream are not really necessary, and they correspond to 0 because there is no convection terms associated with element number 1. And it is also clear that this is the same story or same situation for element number 2 and element number 3. However, for element number 4, there is a conduction term and as well as a convection term, because this right hand side free end is open to the free stream. So there is a convective term to the free end, to the free environment. We can say the element stiffness matrix for the second and the third elements are quite similar, are equal to that of element number 1. So the element stiffness matrix of element number 2 will be equal to the element stiffness matrix of element 3. So as I mentioned before, the element 4 would be different. Element 4, in addition to the conduction heat transfer contribution, there will be an additional convective term due to the heat loss from the flat surface at the right hand side end. So because of that, we need to take that contribution into account. The element stiffness matrix for the fourth element is, let's say, whatever the contributions we obtain from the conduction part has to be summed up with the convective contributions, that is the convective heat transfer coefficient times the area, just to be multiplied by this matrix. Yeah. So now we can directly substitute the numerical values. This is already calculated, and 10 British thermal units per hour feet squared per Fahrenheit degree is the heat transfer coefficient, multiplied by 5 r squared, that is 1 inch is the area, 1 inch is the radius, divided by 12 inches per foot squared, times 0, 0, 0, 1. So you can solve this matrix formulation or matrix. You would get this as the answer for, let's say, the heat transfer coefficient of element number, or the element stiffness matrix for element number 4. So then we have already found out, let's say, the element stiffness matrices. Then we have to use again the equations which we developed in the previous session to obtain the element force matrices. It is clear that in analogous to structural materials, our element stiffness matrices we related to F is equal to K times D. So K refers to the element stiffness matrix, F refers to the force matrix, and D refers to the displacement. Here we have to relate the displacement in the sense the analogous displacement. Analogous to displacement in the heat transfer problem is the temperature. Element stiffness matrix we have found, and we need to obtain the element force matrices, the F values. However, it is clear that in this particular example, there is no heat source. That is, capital Q is equal to 0. So there is, because there is no heat source, there is no heat flux either, which is induced, let's say, by boundary conditions. So because there is no heat source and there is correspondingly no heat flux, there is no convection, there is no convective except for the right hand side. So there is no convection term. So if we think of these force matrices, the elements, if we consider the first element, the force corresponding to the first element, and the force corresponding to the second element, as well as the force corresponding to the third element, are equal, and which is equal to 0 because there is no heat flux, or because there is no heat source. However, for the fourth element, there's a different case. There will be convective heat transfer from the free end. So we have an equivalent force element, which is nothing but the convective heat transfer coefficient times the free end temperature times the area multiplied by this column vector. If we substitute the answers, we would get 10 British thermal units per hour feet squared per Fahrenheit times 10 Fahrenheit degrees free stream temperature 5 R squared multiplied by the column vector. All right, once you do the math, you would get 2.182. This as the answer. It is for the force matrix of the fourth element. Okay, now we have found the force matrices for these elements, and we have already found the element stiffness matrices for each element. Now we can proceed in order to find the, remember our objective is to find the temperatures at the corresponding locations, or temperatures corresponding to node number 2, 3, 4, and 5. So according to the let's say fundamentals of this finite element formulations which we learned, the next step is to assemble the total stiffness matrix, total structure stiffness matrix. We can use the direct stiffness method. Yeah, you can write down the element nodes corresponding to each element stiffness matrices corresponding to each element with the help of the nodes, and then you can assemble the total structure stiffness matrix. I will not go into details because we have already dealt with enough examples, and we have already dealt with how to use the direct stiffness method to construct the total structure stiffness matrix. So I will directly write down the solution here. You can carefully check it out when you really work out this example, whether you get the correct result. So we can assemble the stiffness matrix and write down the total structure stiffness matrix, and with that of boundary conditions here. Okay, the total structure stiffness matrix can be constructed, if you get it clearly, if you it would be 5 by 5 matrix, and if you do your math correctly or do the construction or apply the direct stiffness method correctly, you would get this matrix. This the total structure stiffness matrix multiplied by the corresponding temperatures T1, T2, T3, T4, and T5, which is equal to the force matrix. F1, let's is that unknown. There is no heat flux, so there's if the corresponding element for 2 and 3 and 4 are 0, and at the free end, fifth node, it is corresponding to 2.812, which we just found. So we have the total structure stiffness matrix and the corresponding temperatures related to the force matrix. Here, the F1 value corresponds to an unknown rate of heat flow, which is present at node 1. Let's say if you compare with a structural, let's say, element or structural problem, it is analogous to an unknown support force in a stress analysis problem. Yeah, if there's a fixed end of a support, then we write, if this is unknown, we write it as F1x or F1y. If there are two contributions if it is in two dimensions, we write F1x and F1y. Similarly, since we are dealing with only one dimension heat transfer coefficient here, and the unknown rate of heat flow at node 1 is attributed by F1 value. So we have, let's say, known nodal temperatures boundary, of course, at T1. We know T1, at T1 it is 100 degrees, 100 Fahrenheit degrees. So all the other nodal temperatures are unknown. For these non-homogeneous boundary conditions, we can use the same procedure which we have already used during the stress analysis problem. Quite, let's say, an elegant way of solving this matrices. We can modify the matrix according to this following way to solve the this matrix. Yeah, what we do is I will first explain what we do, and then I will write down the answer. What we first do is, maybe I write down the first solution, and then we can discuss, so it will be clear. What we have to do is simply modify this total equation. We arrange it in such a way that we are able to obtain the solution clearly. Otherwise, we would have to take all the burden of calculating the inverse values. And specifically for solving non-homogeneous boundary conditions, we have to use this procedure, right? The method we propose is that we try to make the first row, first element to be 1, of course, and the first column, first row, all have, let's say, 0 values, except for the first element. All the remaining terms are 0 in the first column and first row. Then the remaining parts of the matrix will stay the same. So all the remaining part of this element stays the same. Only the first column and first row, the first element, first row has only been altered. Easy to remember. The first element is 1. The remaining terms in the column, first column and the first row are set to 0. And on the right hand side, let's put the temperatures T1 to T5. And now the first, when we consider the force matrix, I will write it down and maybe I can explain. The first term we set to 100. Let me highlight the terms which are changed now. This term and this term, and of course this term. These are already changed in the modified set of equations. So we modify the stiffness or the conduction matrix, and of course the corresponding force matrix. Here the terms in the first row and column of the stiffness matrix corresponding to the first term in the first column, first row and first column of the stiffness matrix. It corresponds to a known temperature condition which is equal to 100 Fahrenheit degrees. That is, T1 is equal to 100 Fahrenheit degrees. So we have set it equal to 0, except for the main diagonal, which is equal to 1, which is set to 1. All the remaining terms are 0. Only the first term is set to 1, right? And the first row of the first matrix has been set to equal to, let's say, the known nodal temperature at node 1. You can see 100 Fahrenheit degrees has been set on the right hand side for the first let's say, as the first element of this column matrix. So, of course, the second element in the force matrix has also been replaced. Yeah, if you look at closely, it is being replaced using this equation. Oh, you may wonder how we got this 52.36. It is nothing but what you get when you multiply minus, let's say, 0.5236 by 100 Fahrenheit degrees. You would get minus 52.36 degrees. Here in the original matrix, you can see this element is 0.5236. So in this methodology, we have to multiply this element also with the known nodal temperature, 100 degrees. And because we take it on the right hand side, the minus sign becomes plus. That is why we have used plus 52.36. So on the left hand side of the equation, you get minus. Second, up until the fifth equation is corresponding to rows of, let's say, unknown nodal temperatures, which can be now solved using the Gaussian elimination procedure. Yeah. So simply, you can only select, because of this formulation, you can simply, since you know the value of the T1, of course, the remaining terms, the T2, T3, T4, and T5 can be now easily solved using this Gaussian elimination procedure. It's quite simple. We can, with the help of this solving this equation, you can get these values. So when you solve this matrix, you would get T2 to be equal to 85.93 Fahrenheit degrees, T3 equal to 71.87 Fahrenheit degrees, T4 57.81 Fahrenheit degrees, T5 43.75 Fahrenheit degrees. We have obtained the temperature distribution along the length of the rod at, let's say, distance intervals of 10 inches, which correspond to nodal points using when we use the finite element model. And of course, this is the solution that we would like to get when we use a one-dimensional finite element, let's say, so to say, problem. As you can see, it's nothing new, quite straightforward. The formulations and the procedures are quite similar to that we obtained, or that we used during, let's say, the previous sections when we dealt with structural problems. Maybe we can work out two more examples so that you will be thorough with these formulations. And of course, since the British thermal, so the imperial unit seems to be a bit, let's say, so since you have already had some exposure with respect to how using and converting with the British thermal units, let's move into using SI units and of course try to solve some two different types of heat transfer problems. Then you will be quite confident with handling these problems. So let's consider example 9.2. And in this particular example, let's consider a wall which is 1 millimeter thick. And this wall, let's say the left-hand surface of this wall is maintained at a constant temperature. And another surface, the other side, is insulated. And you are required to determine the temperature distribution through the thickness to the wall thickness. Okay. So this is the problem. A wall where one end is insulated, the other surface is exposed to 200 Celsius degrees. The length of this wall, let's say the thickness is 1 meter. Let's assume a point heat source within the body. And of course, this one-dimensional heat transfer problem, measure x, the distance to the right hand side. So whenever we have a problem, so this is a 1 millimeter thick plain wall. The left hand side surface of the wall is, that is where x is equal to 0, is exposed to or maintained at a constant temperature of Celsius degrees. And the right hand surface where x is equal to L, that is equal to 1 meter, the surface is properly insulated. The thermal conductivity of the wall material is 25 watt per meter per Celsius degree. Now we are using SI units, and of course there is uniform heat generation inside the wall, which we have denoted it via Q. Q is equal to, let's say, 400 watts per meter cube. So based on these conditions, we are required to find the temperature distribution throughout this wall thickness. And for this, we require come up with a discretized finite element model. So as we did in the previous example, we can come up with a discretized model. Let's develop, let's segment this total 1 meter thickness is to equal components. 4 equal components having length of 0.25 meters. We have 4 elements, meaning we have 5 nodes. So the first surface is exposed to 200 Celsius degrees. And the other surfaces are, of course, you can see it's properly insulated. We're interested in one-dimensional heat transfer in this problem. So we assume the heat transfers only in the x direction. So with the blue color, I have represented the insulation layer surrounding the wall material. So in this problem, this is approximated, as I mentioned, as a one-dimensional heat transfer problem. We have already shown the discretized finite element model. So in order to make our life easier, let's consider 4 equal lengths of the elements having a cross-section, having a unit cross-sectional area, that is area of this cross-section, we assumed it to be 1 square meter. A unit cross-section represents a typical cross-section of the wall, so it is representative. So the perimeter of the model, the perimeter of the wall is then insulated to obtain the correct boundary conditions. We can follow the same procedure as we did in the previous case. First, let's try to calculate the element stiffness matrices. For that, let's try to calculate the common factors. Whenever we have conduction, we have these terms: the area, the thermal conductivity multiplied by the length of the element. The area is 1 meter squared, which is the unit thickness or unit area which we considered when solving the examples, multiplied by the thermal conductivity of the material, 25 watt per meter per Celsius degree, divided by the length of the element. Now it's 0.25 meters. We would obtain 100 watt per Celsius degree. So for each identical element, then we have the stiffness matrix to be 100 times the corresponding matrix, symmetric matrix, right? Why did we use this? Because there are no convection terms, that is the H value is equal to 0, so there is no convection contributions to the element stiffness matrix. So the element force matrices, then we have to find with the help of, let's say, the heat source also. So we know the Q value is equal to 400 watts per cubic meter, and of course the heat flux is 0, and the convective heat transfer is also 0. Then we are now interested in calculating the element force matrices. The element force matrices matrix corresponding to a heat source now, because the heat flux is 0 and the convective heat transfer is 0, but we have a heat source term, the corresponding force element for a heat source, whenever we have an heat source, is Q times AL divided by 2. If you can recollect from previous session. For a typical element, then we can calculate, let's say, by evaluating this equation, one corresponding to a heat source for a typical element, such as element number 1, we can obtain the corresponding force elements. If we consider element number 1, we have two nodes, of course, F1x and F2x are the two force elements. Q stands for the heat source, that is 400 watts per cubic meter, multiplied by the area, 1 meter squared, times the length, 0.25 meters, divided by 2. We would get the answer as 50 watts as the force element. And of course, the force matrices for all the other elements are equal to the same values or same element formulation as given here. So next, since we have already then found out the element forces, the forces element force matrices, we can relate it to the total structure stiffness matrix. For that, we need to assemble the total structure with element matrix based on the element stiffness matrices. Yeah. So you can use the direct stiffness method, which you are quite familiar by now, and you can construct the element stiffness matrix, and you would get, if you do it correctly, you would get something like this. Let's take 100 out, which is a common factor. We have it is a 5 by 5 matrix. So F1, since we know it is exposed to, let's say, 200 degrees, there will be an additional term coming, plus 50. And all the other nodes, we have two contributions from either element. So it will be 100 in each case. And of course, for the last element on the right-hand side, it would be only 50. Yeah. So now, because these intermediate elements, there will be contributions from either side, so which will get summed up. Of course, for the last element, it is only one surface. There will be only 50 watt for that force element. And of course, the first surface, there will be an additional term appearing due to the set temperature, the constant temperature. Right. Now, just as we did before, we need to, in order to apply the Gaussian elimination method, we need to slightly modify the equations, or this set of equations, so that we can obtain the results quite conveniently. For that, what we do is we apply the known temperature by substituting the known temperature, that is T1 to 200 degrees, into this equation, and dividing both sides of this equation by 100, because there's a 100 common factor, and transposing the term to the right hand side, we will get the following formulation, which can be solved by really solving equation number, solving a set of simultaneous set of equations. What we do is we divide it by 100. Yeah, we set, as we did before, we know T1, T2, and T3, T4, and T5. We know the temperature T1 is equal to 200 degrees. So we have to, if we use 200 for that as the first term, 200 Celsius degrees. And as the second term, you can see that is, we have to use, let's say, 201 here. The second term would be 201. From third term onwards, we divide it by 100. We get, yeah, you can see that from the third term onwards, we divide it by 100, and you 1, 1, and 0.5. So this is the common factor, because of the common factor we had divided by 100. So once again, what we have done is we have substituted the known temperature 200 degrees, and we divided both sides of the equation by 100 degrees, but by 100. And then by transposing the known terms to the right hand side, we would get. So what we did was we made the first element of the first column and first row to 1 and set all the other elements, other values to 0. Then so the -1 which appeared here, of course the second term should be 200, then +1, because there's always -1 which appeared on the in the first in the so as the second element on the first column. So that is why it is 200 plus 1, 200 minus 200 plus 1 is 201. So that is why you see the 201 sitting in the second column. So since this element now has been changed, so these are the elements which are changed now. These have been changed. All the rest remain intact, right? So 2 minus 1 0 0 minus 1 2 minus 1 0 0 0 minus 1 0 2 minus 1 minus 1 1. Right now we can solve the equations from the second to fifth equations. We can solve them simultaneously, and when you solve them you would get temperature T2 to be 203.5 Celsius degrees, 3 206 Celsius degrees, T4 207.5 degrees, T5 208 degrees. Okay, so we can use these temperature values in this equation, or in this matrix where we have capital F1 appearing, to find the heat flow from the left hand side. We can obtain this, use these equations and the values that we obtain for these temperatures, where we can say F1, the heat flow from the left hand side, is equal to 100 times T1 minus T2 minus 50. 100 times T1 is now equal to, we know, 200 minus 203.5, that is T2 value, minus 50, would yield minus 400 watt. Okay, so now we have conveniently calculated the temperature distribution along the length of this element, along the thickness of the wall. And yes, of course, maybe from the, based on, let's say, the closed form, I'm sure that you have already followed some heat transfer courses, and you are aware that we can obtain a closed form solution when we are interested in calculating the heat transfer through a thickness of such bulk material. Yeah, so the closed form would yield the temperature along the x direction is QXL divided by KXX. I will not go into this derivation, but it is something like this. You can plot this, the results which you obtain from the finite element formulation and also from this analytical equation, and compare the results to compare how well your finite element model predicts the temperature along the distribution or the length distribution of the element. You will see that it is quite, whenever you have time, you can do it and check whether you get the same results, whether you are able to follow the same closed form solution, or whether there are assumptions, especially when we consider the if you can remember, when we derive this model, we assume the temperature, a linear temperature distribution for this particular case. So obviously the temperature within an element will vary linearly, whereas this analytical form gives kind of like a curve So obviously, the analytical solution will provide a graph like that, and the corresponding finite element formulation would follow this graph at corresponding points. But mind you, due to the assumptions that we have used in deriving this, the temperature distribution. So here we are now interested in calculating the temperature as a function of the length x. So you see, if you plot the finite element results obtained, the numerical values, and compare with the closed form solution, which is given by this equation here, you would see that the temperature distribution, the finite element model, somewhat follows closely the temperature distribution given by the finite element, given by the analytical form. But however, due to the assumption we made in deriving this finite element formulation, we assumed when we derive the shape function that the temperature within the element varies linearly. This is exactly what we see here. This is linear, not a cubic or quadratic distribution. It's a linear temperature variation within each element. Yeah, this is what we see as a result. So the more number of elements we use, we will be able to have a fine discretization, and we will be able to follow this close as much as possible, so to improve the results. So before we let's say, before I encourage you to, let's say, before I allow you to go ahead with reading two-dimensional finite element formulations and how to deal with line and point sources, these are quite straightforward and similar to that you used when we dealt with the structural problems. So because it's the same theory, same formulation, I will not go into details. It is the same method applied to different applications. Yeah, so we don't need to repeat the same thing. Before we wind the session today, let's do a final example, again relating to a heat transfer problem. Because all this time we were dealing with structural problems, let's focus more on heat transfer problems. And let's try to see a different problem now. So the final problem, let's say, when we talk or when we discuss in terms of the heat transfer problem, let's consider again a fin, kind of a fin, which is of course used in heat sinks. And let's consider this fin to be insulated on the perimeter. And yes, we can assume an insulated fin rather, insulated fin, where it is subjected to, let's say, heat flux. You know, if it's a fin, it is it can be subjected to heat flux of 5,000 watt per square meter, and on the other end it has a constant temperature of 100 Celsius degrees, constantly maintained at a given temperature. The cross-sectional area, let's assume the cross-sectional area to be 0.1 meter squared. Okay, so the fin, of course, is insulated the perimeter. The left hand has a constant temperature of 100 Celsius degrees and a positive heat flux of 5,000 watt per meter squared is directed on the right end. Let's assume the thermal conductivity of the material to be 6 watt per meter Celsius degree or Kelvin. The cross-sectional area to be 0.1 meter squared. So we are requested to determine the temperatures. Let's assume the length to be L. We are requested to calculate the temperatures at L divided by temperatures at L divided by 4, L divided by 2, 3/4 L, and at L. Yeah. the complete length of the element or the fin is 0.4 meters. So yeah. So now we can use the stiffness matrices which we derived previously. Since this is governed by the conduction, we only have the conduction term coming into play. The second term, of course, this convection term is set to 0 because there is no heat transfer by the convection from the surfaces, because the surfaces are insulated at the perimeter. And of course, there's constant temperature on the left hand and also constant heat flux on the right hand side. So we have, let's say, if we think of the length, 1, 2, 3, 4, L divided by 2, L divided by 4, 3/4 L, and L. We have 4 elements, 1, 2, 3, 4 elements. So let's write the stiffness matrix for each element. K1, K2, and K3 is equal to AKXX divided by L times 1 minus 1 minus 1, 1. So A refers to 0.1 cross-sectional area meters squared times K is 6 watt per meter per Celsius degree divided by the length is 0.1 meters. 1 minus 1 minus 1, 1, 6. The result would be 6 minus 6 minus 6 and 6 watt per Celsius degree. We know that the K1, of course, K4 is also equal to K1. Yeah, because this always there is no convection taking place, because there's always a set temperature on the left hand side and of course a heat flux on the right hand side. So it is only the conduction which governs. So basically all the elements have the conduction term corresponding to this heat transfer problem. Now we are interested in calculating the force matrix. For that, we know the force element of 1, the forces corresponding to element number 2, and the forces corresponding to element number 3 are 0. Why? Because there is no heat generation, there's no internal heat source, and of course there is no surface heat flux either. However, for the fourth element, we see there's a heat flux. So we have to accommodate that. Q times A, we can accommodate it using this equation, where Q is equal to 500 watt per square meter multiplied by the area of that particular element, that is 0.1 meter squared, 0, 500 is the resulting. This is the result you would get if you solve this. So now we have the stiffness matrices for each element, and of course we have the corresponding force matrices. Then it's the same protocol again. You assemble the global stiffness matrix and the global force matrix. We obtain the global equations like this. If you use the direct stiffness method, of course, you would get this. All right. So by assembling, we get a symmetric equation. Of course, this part is symmetric, and the corresponding temperatures, we know T1 to T5, and the respective force matrices, where F1, the force at 1 let's denote it as F1x because it is exposed to a constant heat flux. Second term 0, there are no internal heat fluxes, and the last term is we know it, so to say, the 500 watt value which we just obtained from the previous equation. Yeah, so now we can apply the boundary conditions. Boundary condition on the temperature where T1 is equal to nothing but 100 Celsius degrees. Yeah, so we can substitute this value which we get T1 in the previous set of equations and solve the second through fourth equation simultaneously, which is associated with unknown temperatures to T2, 3, T4, and T5. In solving this matrix, we will get simultaneous set of equations. We can solve them and obtain the temperature values from T2 to T5. So T2 would be, if you do the math right, you could get 183.33 Celsius degrees. T3 266.767 Celsius degree. T4 350 Celsius degree, and T5 433.33 Celsius degree. So by substituting the nodal temperatures into these equations, the first equation, so to say, which will result from solving from the simultaneous set of equations generated by the matrix, we will be able to get the heat source at node 1, which corresponds to F1x. F1x would now be equal to, let's say, 6 times, if you solve this matrix, 100 degrees minus, that is T1 minus T2, 183.33 to be equal to minus 500 watt. Yeah, so you see the total heat source given from this has to be as a negative value, which means that the heat is leaving from the left hand side. The heat enters from the right hand side, leaves from the left hand side. So this the source is the same as the source coming into the fin from the right hand side, which is given by, let's say, Q times A, of course, 500 times 0.1 is a square area, is 500 watt. So you see that the energy conservation, heat entered on the right hand side, leaves as a negative value from the left hand side. So it is quite clear now that we are able to tackle heat transfer problems using the finite element method. And of course, we see that it is really a very useful method now, especially when it comes to dealing with complicated problems where we don't have closed form solutions or complicated problems with having different materials, specifically where we don't have a direct, let's say, where we cannot do a simple hand calculation with the help of analytical equations to find the temperature distributions within a body. So you saw when we did a comparison with the closed form solution, and that we obtained from the, let's say, finite element simulations, it seems to provide a good agreement, apart from the fact that the deviations which we observe due to the approximations which we made when deriving the elements, so elements, shape functions of the elements. Since this is closed forms, obtaining solutions using closed forms are difficult, if not impossible. This method is quite useful when you are using to solve heat transfer problems. And of course, you will be using them now in your mini projects. You will see how convenient it is and how complicated structures and analysis can be conducted using this finite element method. So it's quite elegant, and now you are really competent of handling heat transfer problems using the same finite element procedure. This, I would like to wind up the session for maybe post some more examples on heat transfer problems. You can try them on your own, and if you have any questions, you can come back to me. I will post some reading materials on two-dimensional finite element formulation, as well as how to deal with point and line heat sources. These are quite similar to what we learned during the structure, what we applied for structural problems. So it's the same methodology, different application. I will not repeat here.